Hello again, it's Cal from Wise Guys Tutoring, and I'm back to solve questions 11 to 16 of the EmSAT Math 2022 specimen paper that's found online. I think these questions are a little bit simpler than the ones that we were doing from 1 to 10, but you will be the judge of that. I'll remind you that I do offer private lessons and group lessons for the EmSAT Math, so hit me up on Instagram at WiseGuysUAE or by email info@wiseGuysUAE.com. Okay, let's get started. Question 11 says, the speed of light in a vacuum is 299,792,458 meters per second. That's fast. Which number, written in scientific notation, is the best approximation of the speed of light? So let's talk about scientific notation first of all. What is it and why do we use it? So think of big, huge numbers, something like, speed of light, or let's even say a planet, right? Or some kind of star would be 103 million kilometers away from our planet, and then something like the size of the orbit of Neptune or something is 12 million or 112 billion, some huge number like this. Okay, these numbers, when you're dealing with big large numbers, can be cumbersome, it can get tricky, and it can get, you can make a lot of mistakes comparing these numbers and adding them and such. So we use scientific notation, which basically has one rule. You need the number to be between, to be between 1 and 9 inclusively, so no zeros and no tens, and you combined with 10 to the power of something, and I'll show you what that looks like. Let's use this number that I put up here. Okay, so 103 million is a very big number, and we're going to rewrite this in scientific notation. Now when you don't see the decimal point, it's right here at the end. To make this number using one digit and combined with a multiplication of an order of 10, this is what you do. You say, I'm going to move my decimal 1, 2, 3, 4, 5, 6, 7, 8 spots. So it will end up right here. So my scientific notation for this number, the equivalent will be 1.03 times 10 to the 8. Okay, these numbers are exactly the same because 1.03 times 10 to the 8 gives me 103 million. And this is because 10 to the 8 is 100 million. So all I'm saying is 1.03 times 100 million gives me 103 million. Okay, we can use a simpler example. Let's say I have 1,200. and I want to write this in scientific notation. So I use the same technique. I have my decimal point here and I say 1, 2, 3. I move it 3 spots. That means this number can be written as 1.2 times 10 to the 3 because we moved it 3 spots. And if you think about this, what's 10 to the 3? Well, 10 to the 3 is just 1,000. So what I'm saying is 1,200 is equal to 1.2 times 1,000, which it is. Okay, the reason that we do this, let me show you. If I were to do this 12, what did it turn out to be? 12 billion and 1,000. Okay, this number would be, let's take the decimal point and move it again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this number would be the equivalent of 1.2, and then there's a bunch of zeros, 0, 0, 0, 0, 0, 1 times 10 to the 10. Now these two numbers are much easier to compare. I can tell that this one is at least 100 times bigger. It's at least 10 to the 2 times bigger than this number. Okay, so you just have to look at the order of magnitude and I can tell immediately that this one is bigger. This is what you need to look at first when you're comparing them. I'll give you another example. If I have, for example, 6 times 10 to the 5 and I have 3 times 10 to the 6, well, this bottom number is bigger, okay, because you're looking at 10 to the 6. This number here is 3 million, right? And this number here is 600,000. So it's actually not even close. When you look at the order of magnitude, it tells me immediately which one is larger. So that's why it's very useful to use scientific notation when you're dealing with huge numbers, or even if you're dealing with tiny numbers like, wavelengths, right? Wavelength can be really tiny. They can be like 500 nanometers or something like that. It could be this small, and again, a bunch of zeros is long to write, and it gets tricky, confusing when you're trying to compare them or add them or multiply them. So what you would do is you would say this is 5 times 10 to the minus 7 meters, right? How do I know that? Well, look at my decimal. I'm going to move it to the right. 1 2 3 4 5 6 7. Remember, we have to get the first digit has to be between 1 and 9 inclusively. But since I moved it to the right, I'm going to say it's minus 7, right? Because it's 5 times 10 to the minus 7. This number 5 gets much smaller. Whereas here, when you're moving your decimal to the left, you use a positive number because your number is getting bigger. Okay, so that's how you use scientific notation. So let's get back to the question. First of all, it's an approximation they're looking for. And if they're saying it's an approximation, then I can safely say that, this number can be approximated by, you probably guessed it, we could say that's about 300 million. So if this is about 300 million, and I want to do this, write this in scientific notation, I'll take my decimal and I'll say 1 2 3 4 5 6 7 8. So this number is the same as 3 times 10 to the 8, which means the answer is A, or the first one. All right, let's move on to question 12. Okay, what is the definite integral that represents the area of the region bounded by the graphs of the functions below? y1 equals 5 minus x squared, and y2 equals minus 3x minus 5. So when you're finding the area under a curve, I believe we've spoken about this in a previous question, which I'll put up again, the integral is what's required. You're finding the integral of a function. We say the area under the curve, but actually if you were to take the integral of, let's say, this curve between this point and this point, then what you'd be finding is the area under your curve, or between your curve and the x-axis. This would be the integral of, for example, minus 2 and 5. Okay, and if this line was called y equals 2x plus 1, then this green area, the green area would be found by calculating the integral between minus 2 and 5 of 2x plus 1 dx. So you find the integral and you evaluate that integral. Okay. For now, though, that's not what they want. We have two curves, we have two graphs, and we have to find the area between them. I've taken the liberty of graphing it out, and let me put that on the screen. There we go. So these are the two graphs. The red one there is 5 minus x squared, whereas the blue one is minus 3x minus 5. Okay, so we want to find the area between them, which would be this green area here. And whenever you're looking for an area between two curves, what you have to do is do the integral, okay, wherever they intersect. Let's call this A and let's call this B. So you would always do from A to B the integral of the top function, which for us is y1, minus the bottom function, which for us is y2. Okay, you always do top minus bottom. If they were, sideways, right and left, then you would do the right minus the left. For now, let's do this integral and set up and see if it looks like one of these. So we're going to do the integral between which limits. So we need to see the area bounded by them. You have to first find where do they intersect. Right? Now I've drawn it graphically and we can tell what it is. But if you're looking for the intersection, we'll do it here on the side. I've just put in the previous video how to find intersection. When you have y equals something and y equals something, and you're looking for the intersection, you have to equate them. Right? So you do this one is equal to this one. When are they equal? This x value for both will give the same y value for both. Okay? So to solve this quadratic, I'm going to put everybody on the other side. So I'm going to say plus x squared minus 5 on both sides, right? These cancel out. So you end up with 0 equals x squared minus 3x minus 10. and you're going to try to solve this. The easiest way to solve this one is by factorization. You find two numbers which multiply to give you -10 and which add up to give you -3. So you rack your brain and you figure out that it's probably -5 and 2. You come back here and you put these in here, x minus 5. I'll put a link right now for how to solve these quadratics. There's a number of techniques and I'll show you the video for this one. And x plus 2, okay? What this means here is my 2 points, the two values of x that make this equation true are x equals 5 and x equal -2, okay? So those are the x coordinates of my intersection. And you can tell here, this is in fact -2 and this one is +5, okay? So you do the integral from -2 to 5 and you put your equations in. So the top one is -5 minus x squared, pardon me, minus -3x minus 5 dx. So you do a little rearranging here and you find you got the same limits, and then you say 5 minus x squared minus -3, that's plus 3x, minus -5, that's plus 5. So then you can rearrange it a little bit and you end up with, from -2 to 5, you have minus x squared plus 3x and plus 10 dx, which looks exactly like that first one. Okay, so that's how you find the area between curves, or the area between under one curve and the x-axis. You need to find the limits first, right? The limits where you're looking for. For us, it's the intersection of the two curves. That's what we did first, to find the limits. And then you subtract. You do the top curve minus the bottom curve, and you find the integral. That's how you find the area. Okay, let's move on to 13. Okay, next one. In nature, biological growth is modeled using exponential equations. To determine the population density of a certain type of non-native plant, the number of plants n in an area at a time t, where a and b are constant, is modeled by the function n of t is equal to a times b to the power of t. The table shows two values of the function for a certain non-native plant. Which equation can be used to find the number of plants in an area of time? Okay, so let's talk about the exponential form first. So what we've usually been working with is linear, right? It looks like a line. This is like, your phone bill or something. You pay $10 to subscribe, and then every 10 minutes that you use, you pay an extra $5 or something. So this one goes up linearly, right? It goes up very predictably and it goes up constantly at the same rate. But some stuff is not like that. For example, population, like world population even, right? Because there's more and more and more of us and more people to reproduce, whether it's people or bacteria or plants in this case, the population generally takes this kind of trend, right? It increases faster and faster and faster. It's not a linear relationship. It's not like the population of these plants goes up by 5 plants every hour. No, it goes up faster and faster. First it's 5 every hour, then 10 every hour, then 12 every hour, or whatever it is. It gets faster and faster is the point. So you use exponential to model that. And it's actually really useful and very realistic, okay? Exponential functions, in this case, they've given us the shape. They told us it's n of t equals a times b to the power of t. This exponent only applies to b. B, we're going to call it the growth rate. The growth rate is what we're going to multiply the base by every single time. So for example, if it grows by 5%, right, by 5% every year, then b will be 1 plus 0.05. That will be b, because whatever you're growing by 5% every time, you have to multiply it by 1.05. Okay, that's how you grow by 5%. That's how you'll usually see it. It could be something else. It could be like decrease by 10% every year. Well, in that case, it would be 1 minus 0.1, because that's 10% in decimal. That's 5% in decimal, by the way. So your decay rate here, this would be called a decay rate, because decay means decreasing while growth is growing. So that's how you would find b, okay? This one here, the value of a, this is always going to be your initial value or your initial amount. Okay, it's your original value at the beginning. In this case, it would be like, how many plants did I have in the beginning? If we're talking about money or investment, that would be how much money you had to begin with. Okay, so knowing these 2 points, t0 especially, and another point with t, I can figure out a and b, and I'll show you how. So let's get started. When I say that t equals 0, that means n at 0 is equal to a, which I don't know, times b, which I also don't know, when the time is 0. Now the good news is, I know what n of 0 is. They've given it to me. They said it's 150 plants. A, I still don't know. And b to the 0, thankfully we know this property, anything to the power of 0 is actually equal to 1. No matter what it is, to the power of 0 gives you 1. So a times 1 equals 150. Well, now I know that a is 150. So I've solved for my first variable. Okay, so now that I know a is 150, I'll rewrite this equation. I'll update it here in purple. I'll say that n of t is 150 times b to the t. Now the problem is I don't know b yet, but that's where the second clue comes in. When t is 1, I know that n is 450. So I'll say that n of 1 is 150 times b to the 1. Right? And I know what n to the 1 is. N to the 1 is 450. They've already told me, right? When t is 1, n is 450. I know this one is 150. And I know that b to the 1, anything to the 1, is just itself, right? And using basic algebra, I'll divide both sides by 150. And I can figure out that b is 3, sorry. b equals 3. Okay, so now that I have a and now that I have b, I can tell that my full equation is 150 times 3 to the t. And of course, that looks a lot like this one, top right, b maybe, or a, b, c, whatever, that one. So this is your initial value. That means at the beginning of this study or experiment or whatever it is, there was 150 plants. And every 1 hour or 1 unit of time, 1 day, 1 year, whatever it is, they are tripling. They're becoming 3 times as many. Meaning when the time is 2, I know this is going to be 1,350 plants because I just keep multiplying by 3. And you can tell that they grow exponentially, right? It's not like it increased. At first it increased by 300, but then it increases by 900. And then it's going to increase even more by 2,700. It's going to keep increasing a lot. That's why it looks like this. Okay, keeps increasing more and more every time. So it becomes exponential. So when you have the initial value, it helps you, the initial value as in when t is 0, it'll help you find a. This is always the initial value. And b is always the growth rate, right? By how much are you growing? For us here, we're growing times 3 every time. You're growing times 3 every single time. So that's the growth rate. All right. That's it for this question. Let's move on to 14. Okay, this one says, at which of the 5 points on the graph in the figure below are both dy dx and dy dx to the second order negative? Okay, so let's talk about what those things mean. When we say dy dx, that means the derivative. And when we say derivative, when you're talking about a graph in particular, the derivative is the slope or the gradient. Okay, that's what dy dx is. Always when you're finding the derivative, it's the rate of change. Okay, but we use it to find the slope of curves. Dy over dx. That's y prime. Also, it's the same thing. That means the derivative is the slope. Okay, what we're talking about when we do d squared dx squared, which is the second derivative. Okay, the second derivative. The second derivative tells you about the concavity. What does that mean? It means, is it concave downward or is it concave upward? So I'll draw that for you. This is, well, let me draw the graph. This one is concave downwards. and this part here is concave up. Okay, you can tell because it's like a smiley face and that one is downward, right? This would mean that the second derivative is negative. Whereas this one means the second derivative is positive. Okay, so that's what this is going to tell us. So here they're asking me, where are they both negative? So let's look at them one by one. Let's look at A. So for A, first let's check the slope. To check the slope, I go like this. I make a line right where A, it's a tangent line. Tangent to the curve means it only touches the curve at A. So I can tell that this is the slope of the curve. And the slope of the curve is positive. Here it means that the first one, dy dx, is definitely positive. So already A is out of elimination. Just for jokes, let me tell you guys about this. Since it's on the concave, downwards, that means the second derivative here, you guessed it, the second derivative would have been negative. Let's check B, okay? If I do the same thing at B, I'll take the slope at B. Here we go. It's a tangent. It only touches the curve at one point at B. You can tell that the slope is negative because this line is going down. So this part here is negative. So that's good. And let's check the concavity. It's on this part of the curve. So this one also has its dy dx second order is also negative. So I guess we've solved it. The answer is B. Okay. The other option would have been C. And why C is wrong is because you can check the concavity here. Since he's on this part, the part that's facing upward, it's cupping upward. This is concave up, meaning the second derivative here is actually positive. His first derivative, which is the slope of the tangent at that point, since the line is going down, it's actually negative. But alas, it's not enough because you need both to be negative. If you look at E, his slope is positive. That means the derivative is positive, and he's on the, the concave up part. So even the second derivative is positive. So E is not even close. Okay. So the only one that has both negative is B. And that's what they signify. Dy dx, the derivative is always going to be the slope, right? It's the rate of change, so it's the slope. And the second derivative is the concavity. It means, are you concave up or are you concave down? I'll just add one, bit of knowledge here. Let me bring in a fresh graph. There you go. So a lot of times what they use this for, the second derivative, is to see if you have a maximum or minimum. Whenever you have one of these maximum or minimum points, like the vertices, okay, the derivative, the first derivative, will be 0, because as I just said, derivative means the slope of the tangent line, and you can tell that the tangent line at these points, the derivative is 0, the slope is 0. Okay, so that's how you can tell if there's a maximum or minimum. You find the derivative of a function and you set it to 0. But the problem is, how am I going to know if it's a maximum or a minimum? Well, that's where the second derivative test comes in. So you find the second derivative at this point, and if your second derivative is negative, then I'll know, okay, less than 0, as in it's negative, then I'll know that I have a maximum. My vertex that I found is a maximum. And here, if my second derivative is positive, then I'll know that it's concave up. And if it's concave up, that means my vertex here is a minimum. So this is called the second derivative test. Okay, once you find a vertex by setting your derivative to 0, you can use a second derivative test just to check the concavity, which tells me if it's a maximum or minimum. Okay, hope that makes sense. Let's move on to the final question. So number 15 says a square has a perimeter of 88 meters. What is the length of each side? So it's fairly simple. Whenever you have a chance to draw a diagram, you should draw, whether it's geometry problems or word problems. We are very, very visual creatures, and it really helps to draw. Now, it says the perimeter is 88, and perimeter means the sum of all the length of all the sides, right? We've got 4 sides, and this is a square, so it's got this property that all the sides are equal, right? So each side, let's say, measures x, because I don't know what it is. And if I'm looking for the perimeter will be the sum of all the sides. So it'll be x plus x plus x plus x. Now, I've been told that the perimeter is 88. So here it is. And when you're adding variables like this, you just have to pretend they're objects, like they're apples. So it's like 1 apple plus 2 apple, 3 apple, 4 apple. I got 4 apples. To solve this, you divide by 4 on both sides because x is being multiplied by 4. So if I want to get rid of this 4, I have to use the inverse operation of multiplication, which is dividing by 4. This side gets jealous and gets divided by 4. These undo each other, and you end up with x equals 22 centimeters, or meters rather, my bad. There you go. That's it. 22 meters. That was probably the simplest one so far. All right, that's it for this video. I hope you liked it. Make sure you subscribe to the channel and like the video. If you have any questions or comments or suggestions, please leave them for me below. I'll remind you one more time that I do offer classes for the EmSAT Math, so hit me up on Instagram at WiseGuysUAE. Let me know if you need some help, and I'm always happy to do so. I'll see you guys in the next video. Thank you.